On Zoom.
What's that now?
I sent it to me, the three of us.
Yeah, I guess so. Rest of our lives. I don't even know who's in this class anymore. Reed's here, maybe. That's me, maybe. That's it, 5, I think. 4 enrolled, maybe.
Sarah's with him.
Oh, yeah, Sarah's still here. In the class. I think she's still enrolled.
San Francisco.
Yeah, it's San Francisco.
Giselle's wedding.
What's it?
Giselle's getting married
Ah, shit, I forgot that's the
on Friday.
soon. Couldn't be me, alright. Alright, how's folks doing? Oh, we're still early, we have 2 minutes. Start? Well, let me see if we got a chalk in this. We have this chalk,
Y'all have observatory tonight, right?
yes,
Okay.
but if you can go, that'd be great. Can't go, that's okay.
No, honestly. No. Who's there?
She likes to go.
Hey,
It's my mom.
I won't be there tonight, so why are you even going?
You're right. Why would I even go? You're absolutely right.
I said, I'm going snowboarding. And I'm gonna hurt myself on accident.
How did you get into like the situation going somewhere?
It's Steve's birthday and we're both friends with him, so we're like, we'll go.
Nice.
But I don't really want to snowboard. So Zori also has it, so I'm just gonna hold on to her the whole time.
Oh, so you guys both want to go to see one?
She wants to go. I'm like, I'll try everything once.
That's fair.
You know it.
I'll see happy birthday.
Okay. Happy birthday, Steve.
Who'd you go with?
Me and Zori and Steve.
Steve, who? Oh, you're that, right?
Yeah.
You only.
I think it's gonna be worse in snowboard than years, right?
Everything you said was recorded.
Yeah, we didn't bad.
I'm gonna listen back to it, just the first 3 minutes.
I did it bad for you.
I would never say about it. I sold my coffee twice in the car this morning. 'Cause it was like filled up to
Well, I
here.
hate that.
At first, I was pulling out of my driveway and it went, and then I pulled over to like stop and it went. It's like, fuck.
The other day, I got like a 100 gallon truck, because for when I went camping, I had it in my car. I lost the cap and then I turned crazy and it's my whole back.
It's pretty good. Okay, so we were talking about numbers. Chris, Monty, you're starting, it's exactly 10:30. What were we talking about? What is the difference between the numbers that we were discussing, a couple weeks ago and what we're gonna try and do now?
Isn't the numbers that
We have like an infinite set now and it's continuous.
no,
I
actually,
like numbers.
we're remember like
I was thinking ghosts.
no, so like now we're doing statistics, so now
Yeah.
we're given, assuming that this comes from like an infinite data set, but then we're only showing like a little fraction.
Yeah, I guess it says single numbers for now. You have n results.
Okay, so we're transitioning to a field called statistics. And the primary assumption, when we think about statistics, is that numbers are generated and there is hidden information. And so the goal of this entire section is to determine mathematical ways to learn hidden information and to assign meaning to it. So we are going to do things like talk about our confidence in the levels of information. And if you've looked at the homework, you'll see that I gave you a whole bunch of numbers. And without knowing anything about the numbers, you will be asked to tell me what the vibe is. Does that make sense?
Yeah.
Okay. So we had all these numbers and I showed you there's more than one way to construct an average. More than one way to skin a, right? And the ways that we use these statistics, a statistic is any metric by which we can form information about a data set. So they are not, I mean, there are some that are most often used, and I'll show you the most popular ones. But you can create your own statistic for your own data set. So because I know here everyone loves baseball, there's an entire field called sabermetrics, which is a field of statistics that has specific statistics designed to investigate player performance. Okay, so any, data set that you might be interested in, you get enough people and enough money, you will form statistics about those things that need to be investigated, right? Okay, so that's the motivation for today. What was the, there was like modes and medians, you have those numbers written down? Yeah. Good, what the mode was any, and what does the mode mean again? Good, and so they all appear exactly one time, so there is no number that is. And was this helpful?
No.
Not helpful. So some statistics are helpful and some are not. What about the median?
189.25.
189.2. Was that helpful?
Kind
Kind of, yeah, it sort of tells us something, right? Okay, yeah.
Just, don't know why I'm so confused on how to find the median, because I thought it would just be like the actual number in the middle, but it feels like you pick the number in between two, maybe.
Yeah, okay, so good point. So there's a difference, right? So there is like, here's the range. And all the numbers could fall in between there. If you grab the middle of the range, that's just the midpoint. Okay, so that's called the midpoint.
I guess just how do you find the median, because I don't know why I Googled it and so.
Okay, so let's arrange these numbers between the range. Let's kind of do it together really quickly. So this will be 166.3. And this is 204.7, right? And so the midpoint would be the thing that you calculate. We take the two ends and you divide them. But let's look at how they're distributed. Okay, here's a 200. Here's the 204. 168 is here. Okay, and 169 is here. Okay. How many points do I have left? I have the 180s. I have 189 and 188. That's over here.
193 and
It's here in
200 is over here.
183.
193 is here. Right?
So how would you find, what is the median?
So is that enough points? 1, 2, 3, 4, 5, 6, 7, 8. Okay, so now what you do is you find the middle of where the points are. So you go from, this is 1, 2, 3, 4, 5, 6, 7, 8. And since there's 8 points, the median is going to be in between points 4 and 5. Right? And that does not necessarily represent the midpoint of the range, because the points are not equally distributed. Make sense?
Yeah,
Cool.
sorry.
Yeah, no, that's good. This is clarification. Okay, so that was the median, and we found means, right? And where were our different means?
Arithmetic, geometric.
Yeah, what was the arithmetic mean?
Just the normal, like.
No, what was the number? Sorry.
180.
What's that?
184.975.
So notice that the arithmetic mean was smaller than the median. So the arithmetic mean is over here. Okay, was that helpful? I don't know. Good point. I don't know. So notice that, there's 3 points over here that are pulling it in the direction. That's the point of the arithmetic mean. Okay, what about the next one?
The geometric mean was 184.
And 184. So that's also right over here. Which one's bigger?
The geometric mean. Oh, wait, sorry, no, the arithmetic, the other mean.
Okay, next.
There's the harmonic mean, which is 183.9.
That's over here.
And the last one is a Ruby square, which is 185.
185, so that's even higher than the arithmetic mean, right?
Yeah.
So we talked about different means when we were talking about the probability of distribution. And what was the other thing that we cared about? Talk about probability distributions, we wanted the mean and the variance. Good, so let's create a variance for this data set. Do that. Call this the sample variance. That would be S squared instead of sigma squared. And it's gonna be 1 over n, where n is the number of data points, times the, times the sum. Here. Might be saying to yourself, what is the X bar?
Oh, that's the average.
Which average?
I think we're.
Okay, we want to be very careful in our words, right? We don't just say average, we say which average. So that is this one. Okay, good. So in order to construct the sample variance, you probably have to construct the sample mean. There's a way of doing it, so you do them both at the same time. But essentially, the sample standard deviation would just be, of course, the square root of that. Good. Make sense? So let's use it. For this data set, what do we have? What do you think? Which? Just S. Just S is 14.
You got 14.17.
That's good enough for you. 14 is pretty good.
And then there was 201.
Good, good. Yeah, that's close enough for my purposes here. So what does that tell us about the distribution of numbers?
Oh, like, yeah, like, you should, there's like, an expected value that centers around your arithmetic mean.
Good,
It should
okay,
vary.
hold on, pause one thing at a time, I'm gonna write this down.
Okay.
So here's our expected value, right? So if we thought about this as all of the distribution, giving us all the information, we would call this thing mu, right? In the probability distribution world. That's not the world we're in, but that's the analogy we're making, good. And then what was your next part?
So with the S, that would be the variance, so that would mean that. Like your data points should give or take fall between like either plus 14 mu or minus 14, or mu minus 14.
Okay, so I'm gonna clarify a couple of those statements, almost all of that's correct.
Okay,
First part is this is the variance and this is the standard deviation,
okay,
okay, just one thing. And then the second part is here, you made an assumption that you didn't know you were making. Okay, so if I go off in this direction to mu plus S, or in this case, if we're thinking about it as a probability distribution, I would call it sigma. And in this direction, I go off as mu minus sigma. Okay. You said that the data should fall in within this range?
yeah, we,
So there's an inherent assumption there built in about whether or not this is a normal distribution,
yeah.
right? Because I think if you finish that sentence, you say, well, most of the data should fit in between that range, but we don't know that, right? This ask is simply a sample parameter telling us about the width of the distribution compared to the data itself, not compared to whether it's coming from a Gaussian distribution. We don't know that yet. In fact, if you look at the data, is it Gaussian? Doesn't look like it would be, right? So what is 185 plus 14? That's 199. Well, I don't know, maybe this is what 200. So this would be the edge right here.
Yeah.
And if I take away 14, it'd be 171. Well, that's interesting. All of these points would not fit. I didn't draw this very good. It's not a very good number line. Right, so this would be mu minus sigma. This would be mu plus sigma. And I have 1, 2, 3, 4, 5 points that lay outside of that. Is that Gaussian distributed?
No,
How many do you expect to lay outside of it?
like,
What?
No,
Like in the
6.
middle?
Yeah.
1 minus 0.6,
Good, which is?
22.
I don't think
no,
so.
30.
32. So let's round. If you have 10 points,
Yeah, 10 point.
if you have 10 points, how many points do you expect to fall outside of 1 sigma? If it's Gaussian distributed,
Oh, so like 3 points.
3. Okay, so this is your first bullshit indicator. Okay, and as physicists, you have to have really good bullshit indicators. If the data is real and it's normally distributed, it will not fit between the error bars.
If it's not.
Ready? Let me show you. Okay. Let's take a data set. Okay. And let's assume that this is time. And this is the number of counts. Or some number that represents a financial quantity. Okay. And let's say you're checking someone's books. You work in the finance tech sector. Okay. And they're showing you what is essentially a line like this. Okay, increasing profits with time. Let's go. And daily you have some scattered up and down around this. Right? Okay. And then I tell you basically the whole time, this is like the 1 sigma envelope. And what that means is just as I drew the line, this was mu, and then this was mu minus sigma, And this is mu plus sigma. Okay, you invest in this company? How much money do you put in? Not all of it, she learned a lesson. So the claim here. Here's the claim. Scattered. Is due to Gaussian. Probability. Of. Consumer. Purchasing. How much? Okay, any red flags? You don't know what to look for. Okay, so it's going up and to the right, that means more money over time, so that looks really good, right?
Yeah,
What were we talking about when I started drawing this?
You said a sentence, I couldn't remember what you were saying.
Okay. So we made, so Rolanda was making assumption or stating something that we have maybe built in. To ourselves, which is that the standard deviation should represent where most of the data points lie. And I said that that was true in the Gaussian circumstance. And there's a very specific number of points that should lie within 1 sigma. 68. So therefore, if I have 10 points, I expect how many of them to lie outside of the data set? 2 or 3, good.
is, so the claim here is that the scattered due to the Gaussian probability of consumer purchases, there should be significantly more scattering outside of the mu plus or minus sigma.
Exactly.
So all the data just clumped up in between 1 sigma.
Does that mean that they might have ignored data and didn't follow the trend?
Yeah, so something is suspect here, right? So this would be a big, I don't know, red, but that would be a big red flag. Right? Because one of 3 things is happening here. Either they're underestimating their sigma, and their sigma needs to be like down here. Right, that would be okay. Or they removed data before they showed it to you, which is suspect. Or all of the data is fabricated. Right?
Yeah.
So I would say not that much until you have a conversation with them, right? Okay, so this is the power of looking at Gaussian distributed numbers, because you know how they should behave if they in fact are independent of one another and due to a Gaussian distribution, right? Okay, let's delete some of this. And let's talk about covariance and correlation. Can I get rid of this stuff? Ready? Okay, so far we've been thinking about individual data points, like that list up there. But in reality, you might have, say, multiple data points, or multiple pieces of information that you're interested in. So for example, let's say we have human beings and we want to test not only how tall they are, but how much they weigh, right? And we're curious whether or not there is a relationship between height and weight. So for every human being, you can measure multiple pieces of information, right? And you can look for this idea of correlation or covariance. People familiar with the idea of correlation? What's the most infamous saying?
Yeah.
Good, all right.
It's not a good causation.
So correlation is not causation, right? But correlation is correlation. So we're gonna learn how to correlate things today. So let's build a metric for covariance. So we're gonna call it sample covariance. Okay. So variance, if we go back to what that word means, variance is how it varies, how it changes within the distribution. And sample covariance here is talking about how one relationship varies dependent on the other. Right? So let's build something. Now we're gonna say we have two variables, it's called an x and y. These will be our two random variables. And we're gonna have n, which is the total number of data points from which the two random variables exist. Does that make sense why that would work? Okay. In practice, it looks something like this. The mean of xy minus the mean of x, the mean of y. And you can write that out as a whole. You can just write 1 over n and the sum of x I y I minus 1 over n squared over the double sum of xi times yi. Okay, so if we plot something, can someone show me? Let's write it up here. So here's some data. What do correlated data sets look like? That is to say, if one depends on the other, what will it look like when I plot them, one against the other? Say x on this axis. Y equals x, right? So if they're strongly dependent, I would expect the data look like that, right? What if they're not?
You probably get like a zero still, yeah.
Yeah, they'd be just dots everywhere, right? What? What? You like the circle?
Yeah,
All right. And what about if one depends on the opposite of the other?
y equals 1 over x.
Like it's 1 over x. Yes. So what I mean by that is, what if one going up means the other goes down?
Oh, and just point the other way.
Exactly. Okay, so you can usually define something called the sample correlation. We're going to calculate these. Sample. Which is R of xy. So you may have heard this term, the R value between two variables. And that is simply this, the variance in xy, divided by the standard deviation in x divided by the standard deviation. Okay. So let's use it. Yay, I love doing a ton of math for one. Okay, person. A, B, C, D, E, F, G, H, I, J. Height. Weight. Yeah, it's in the ground, sorry. Yeah, these are really small people.
And then,
Yeah, this is intended. We're gonna use CPSs or KGS.
yeah, they're not, United States, so. No freedom units.
No freedom units here. All aside. Okay. So I would recommend here, since there's three of you, let's calculate the correlation here between the two. And in particular, what I want you to think about is, I want to know if these two data sets are correlated and how would I be able to know that? So if you look at the data by eye, before you even calculate anything, what do you think?
I think there would be a correlation.
Why?
Because the smaller ones have smaller ones.
Because the smaller ones have smaller ones. That is the definition of a correlation, right? So you are expecting, Isabel, a positive correlation, right?
Yeah.
Okay, no, that's fine. We're just taking feel of vibes, right? So you're expecting the smaller ones to have smaller ones, not the smaller ones to have larger. That would be a negative correlation. Or uncorrelated, or sorry, anti-correlated. Right? So here the expectation might be a positive correlation. Would that make sense physically with what the things I'm plotting are? Taller people may weigh more, right? So it, there could be outliers, but let's have a look. So now I'll ask you to calculate the sample correlation. So I will recommend for this part here that you each take a different sum.
Well, you guys want. Well, do you want to add together X and Y times each other, or add together just X, which is Y? Just pick one, and then I'll pick one, and we'll stick the one with lunch.
I can do this.
Okay, I'll do X.
Like why, and then why is the weight?
Oh, yeah,
You kind
well, I'll do me, oh, height. I'll do height, you do me,
what are you?
oh.
Okay, so. X equals Y.
X.
Yeah, so-
Yeah, one such that. One such. Wow. 2,000. These are the other two solutions. Oh, two tables. Here's the next one.
Capital N in the covariance, that's the total number of data points between X and Y.
So remember, every data point is given as a pair. So
Oh,
n would be all of the pairs in this circumstance, right? We don't want to double count here. So I only have, I think, 10 individuals.
okay.
off of it, I got 6 to 13.
Oh, okay.
Do we need to do,
No, no, because it's all,
Yeah.
they're all equivalent. They use just six.
no, that's V of X, Y, he asked for R of X, Y.
Oh, are.
Which means we now have to do the,
That's excess one, that's fine. But you can use some of the sums there.
yeah.
Like, I understand. You have all the sums, right? Once you have the sums written out, it's not.
Yeah.
Okay.
So also,
No, we have to do that, we can find the mean, and then we have to do the sum of all of, each of them minus the mean squared, right?
Wow, what's that?
This one,
it is S of X and S of Y is the sum of those.
Oh, that's what that is.
this,
Oh, it's the S. Yes, you're right. Sample variance.
Yeah.
Yes.
Here's how you can write, hold on, say you don't want to calculate the sample mean.
well, I don't want that.
Hold on, let's just put the cheat code up. Feel like you're getting very cranky at me right now, okay? Here's sample squared. Just for an arbitrary, that will be x squared bar minus x bar squared.
Oh,
Oh, I do have those sums.
Oh,
So remember when I said earlier that usually you have to calculate the mean and the standard deviation, or mean and then the standard deviation? Well, that's not always true. So you can use this little handy dandy tool, which you can find in your textbook. And of course, you just take the square root here after you've done the two sums.
so the first term is this, is X squared and then averaged out. And
Yeah,
then the
so
other-
that would be something equivalent to this, right? Right, so it'd be like, see how these are written? That's equivalent to this, except for it's XX instead of XY.
so you,
No.
Doing, S of X right now.
for the X squared with the bar on top, we square them, like square all of them and add them all together.
Yeah, so this would be equivalent to the sum of xi squared minus sum of xi. And of course, there's relevant number of n's, right? So you have, this one would be 1 over n squared.
That's like the same amount of work as the other.
You did it pretty quick, right?
I just meant as the other equation.
Oh, okay. Yeah, perhaps. I thought it was a little faster, but maybe not.
You're doing the X off of the one.
I just need, S of Y.
I think I did S one wrong. But I have.
Well, so as long as you do the average of like each of the weights and square them, and then divide it by 10.
Yeah.
Wait, no, wait, no, wait. I think because like,
Oh, no. But you can't square root.
I know.
I barely.
How to get a negative.
because like it can be negative if the y average squared is like greater than y squared average.
Run it
Well,
back.
you should have a square root unless you're just gonna get.
I'm running it, I'm running it back.
It's leaving this y average squared is a bigger number. For y.
How would y average squared be a bigger number than y squared average?
I'm just trying to
It's
explain what you got negative.
Okay, alright, so I don't wanna spend too much time on this, I thought this would go faster, but I'm sorry if it's busy work.
Yeah,
So
no,
let's ask a separate question as maybe you're coming to the end of this exercise. How big can R get? Yeah,
Just up to one,
why just up to one?
either correlated or it's close to it.
Right, but is that something you just know, or can you tell from the equation?
It's a ratio.
It's a ratio, ratios can be bigger than one.
Yeah.
Yeah, it is true. Sample covariance individual. Sample. Also, sample covariance over. The sample.
Let's have a look.
So those are squared up front. For your sums.
Right?
Yeah.
Yeah or no? What? No, what are you talking about, Chris? Okay, can this ever be negative? Underscore root, good. So this is always a positive, right? Positive, positive. So these, the numerator is always giving you the positive, right? Put at the top.
Should the top always be positive as well, or?
I'm asking what, so we're thinking about the different ranges we can get for this value, this R value. Right? We know, we kind of plotted it out there, we said, well, they can be like a cloud, they can go up like this, and they can go down like that. Right? And it is true, actually, that R can only go between 1 through 0 and to -1. But it may not be obvious necessarily from this until you stare at it for a long time. So here I have one data set X times in the data set Y. So the product, right, let's say Y is all negatives for some reason, and X is all positives, then all of their products will be negative. Whereas here, right, these ones X's and these ones Y's, they're gonna multiply in the same way, but when you take the difference, they're gonna do what? Cancel out, right? So this can be as small as, sorry, in magnitude. Can be as small as 0, no correlation. Because none of the points line up with one another, not carrying any weight. Whereas this can be as bad as, you know, this term here being the dominant term when you do the multiplication, and therefore this being -1. So for this data set, actually, you find something like 0.54. So how would you characterize this data set? Is it correlated or uncorrelated? Or anti-correlated?
I would say that it's correlated.
Correlated, good. So full correlation. Of X and Y are equals 1. Anti correlation R equals -1. Uncorrelation, that is to say not correlated, R equals 0. So you would look at this and you would say, there certainly is at least some partial correlation between heights and weights. Okay. Okay. I'm gonna try not to confuse you too much here. But I don't know if that's possible, so we'll see. Is this okay?
Yeah.
Let me leave that up for training when she goes back.
So,
Okay. The estimate.
okay.
What's that now?
About the tangent correlation of Y.
Okay, yeah,
I
yeah.
think it's-
I mean, honestly, right, this is why we have spreadsheets. Spreadsheets do all of this analysis for us, so that we don't ever make that mistake of maybe one letter here or one number here. Okay. Let me hear this as well.
So does that mean like technically if like there was a sample covariance value of like 0.2, it's technically correlated, but not really?
Yeah, I mean, well, depends on how we talk about the things being correlated, right? So for example, all of the words we use, they're very specific. And so, 0.001 is in the direction of positive correlation. Now, would any reasonable person say they're correlated? No, right? So there's these degrees of what we think about as correlation. So we haven't even begun to talk about how certain we are about these metrics that we're creating, because remember, they're kind of like creating them from scratch. So in particular, you say, well, this at least got over the halfway point.
Yeah.
Right? If it was maybe 0.46, you could say it's leaning towards looking like it's correlated. Right? But like 0.3, a reasonable person would say, who can really tell there? Strongly correlated would be like,
Like what?
that'd be fully correlated, good.
Oh, so like 20.
0.8, 0.9, right? Yeah, very good. So it's like a spectrum, right? And it's in both directions. How much do the numbers represent the correlation? Okay. All right, so now let's talk about okay. We're gonna talk about something called estimators. Okay. Okay, everyone's happy with that? All right, so estimators. And I'm gonna try and spend just a tiny bit of time on this to tie it back to what we were thinking about with probability, and then we're gonna jump right into what they actually are. Okay, so let us imagine some population that we're drawing from a random variable X, and this could be multiple random variables, I really don't care, right? So it could be anything that we want. And it has some sample derived from it, which is xi, x1, x2, x3, so on and so forth to xn. Okay. But you don't know what P is. So this is a big fat unknown. Okay. So the central tenet of statistics is to try and estimate values of the underlying distribution without having access to the distribution itself. And that's where we get the word estimators. Okay. So let's denote various parameters, and we'll denote them with the variable a. So these would be parameters of the unknown distribution. Okay. What would an example of an unknown parameter be? Guesses are perfectly okay.
How much dark batteries in the universe?
Okay, very correct, but also, way above what I wanted. Just imagining what are things that we could ask about a distribution, not a real physical distribution, like what is a thing that we could ask about a distribution?
How many coins were there?
Okay, you're both very right. Both very right, but you're thinking about them as real things. Don't think about them as real things. Ask, what can you know about a distribution?
Oh, like,
Oh.
yeah, oh, like the mu value.
There we go, okay, so ideas of parameters might be something like the mean, right? So we could think of that maybe as A0. Okay, what would another one be?
Yes,
Variance.
Very good, the variance or sigma squared, that could be your A1, so on and so forth. So this is an example, right? This is an example of things we can ask. Okay. These are ways of probing the unknown distribution. Okay. So an estimator then, if we think back in terms of our Bayesian analysis, okay, is gonna look like this. Here's the probability distribution P, and I make some measurement X. Okay. Given some parameter set A. Okay. So you're basically gonna be looking at a bunch of probability distributions from which you could define something that you want to know, right? So you sample these all out, given some probability of finding mu or sigma or something. And this could, of course, I mean, this is a vector quantity when you write it in the book, that's the multiplication of all. Okay. Did I lose people there? Do I need to go back? Did I lose people? Okay. Is it okay if I get rid of this, Trini?
Yes.
So here's what I'm gonna do. That is kind of like a lot of words, and we could go into the derivation and show you in practice how it works. But I think we should just do. I think I should just show you some of the estimators. Okay. So the first estimator. And we'll go back to the idea of like bias in estimators and also standard error on estimators. Like confidence limits, how well can we be confident in our estimators? But the very first thing we want to do is talk about the most basic estimator, okay, which is called the population mean. You've said the word mean and average so many times, it's losing its mean. All right, so here's the population mean. Okay, and the major distinction here is that the population mean and the underlying mean are not the same. So the population mean would be a okay, so let's talk about a population P of X, which has mu and sigma. Okay. An estimator, and we're gonna draw it like this with a little hat. Okay. This thing is going to be giving you sample mean. And it's trying to investigate the population. Right? There's some fun math we can do to show what the expectation value of this on a random sample would be. And that is that you can take the expectation value of the mean And if you imagine that you could take as many samples as you want forever and ever and ever, you count them all up, what would you expect the expectation value to be? Just mu, right? Yeah, it's the real mean. You would hope that it would be that. And here's the one that's maybe not as obvious. What would be the variance in the population mean as we take more and more observations? Yeah, good. It would go down, but how? So this is an underlying property of the population itself, but it's gonna go down like 1/n. Okay, so what did we actually say here? So there are biased and unbiased estimators. What that means is, when we're sampling the mean, you are mostly getting the correct idea of what the mean is. But the standard deviation depends on how many samples you took. Right? So here's a great example of, if I take, maybe here's some population distribution, and I just take 4 pieces of information from it. How confident can I be in knowing the population mean?
So,
Okay, maybe I should have brought the dice. Okay. You have something that you're sampling. And I sample it once. And I take some number of observations and I figure out the mean and the standard deviation. Good. Put that away. Then I do it again. I sample it again. And I get the mean and the standard deviation. Okay. And I do it again. And I do it again. So now I've measured it 4 times. I have 4 values of the mean. The expectation of that mean should be the mean. Good. Okay, so we're getting closer.
Yeah.
But what is the variance on the mean? How much is the mean itself varying? Every sample I take, I'm getting a slightly different mean, and there's some population growing, right? So another way of saying this is the uncertainty on the mean that you're deriving. Now, uncertainty is not really correct in the right way of saying this. We're saying it's an estimator of the sample population, right? Or sorry, the sample mean from the true population. Okay. So what happens here as n gets really large? Goes to 0. Great, right? Because then we would approach, right, confidence. This thing becomes small, very confident. How many observations do you be confident in something's standard deviation? If my God, folks, no, incorrect.
Enough.
1 billion? Okay, will one do?
No, definitely not.
Why not?
So then it's just signal over more.
What's that?
You have a bigger variance, it's just.
It depends.
It depends. So it depends on what we're going for. So if we're doing an estimation of the mean here, right? And let's say I get some number. Okay, the uncertainty on the mean will be as large as the uncertainty in the population itself. Right, the standard deviation of the underlying distribution. So at the very beginning, if I take only 1 sample, it's perfectly okay. But I have to report that my mean here is plus minus the standard deviation. I am that unconfident. Now, if I do it 3 or 4 or 10 more times, then it goes down dramatically, right? I can take my standard deviation that I sampled, right? I can shrink it. You see? Yes or no?
Yeah.
Okay. We can write this in terms of the Gaussian form. Or no, do you want to see that? Okay. So in terms of this format here, we're going to write the population of the sample mean here in terms of mu, which would be the population mean, and the sigma, which is the standard deviation of the population, underlying population, assuming in fact, of course, that it's given by the approximate Gaussian form. Let's do it like this. Here. You see how that could work there? No, okay, so this is telling, so let me just walk you through what I did. So I said, if we assume the population is large enough, that we can treat it as though the central limit theorem applies. And if you recall from the end of Monday's class, I was talking about the central limit theorem, which is basically when you start adding enough data and it's uncorrelated, and these other 4 things that I talked about, almost everything starts to look Gaussian. Well, that's really convenient, because as long as it looks mostly Gaussian, and we can cram it mostly within the tenets of the central limit theorem, then we can describe the population distribution function, probably with a Gaussian, which has something like a sigma and m. Right? And so if we have these parts here, the parameters that we want to know about, say mu and sigma, then we can estimate the population uncertainty given those. Right? This is the probability of these given the others. Okay, so that was fine, but we didn't really like it, so let's make it worse. Now let's talk about the population sigma squared. This is the population variance. And here it's not so straightforward as like this 3 lines were. Mostly because we don't know the true mean. So if you want to do something like the variance, which is to compare the data point you have to the true mean and see how far off it is, if you don't have a good estimate of the true mean, then how can you possibly construct a reasonable estimate of the variance, right? You're really going to be comparing to the sample mean, which may or may not be close to the true mean. So in fact, we have this wonderful symbol here. Here's our sigma squared with our hat. Okay, so this is going to be 1 over n, the sum of x minus mu. Okay, everyone's like, that's not difficult. What are you talking about? Come on. So let's break this apart. This is 1 over n sigma x minus squared minus mu squared. Right? So that's great. But it's only great in what circumstance?
You only have like, we only did the trial once, but if you have like a,
Even harder than that.
when you have a low variance.
So this is only true if mu is known. I told you it'd be tricky, right? So what do you have instead? If it's unknown, you have to replace this
Population.
right? You have to have something to compare it to. So let's replace it with x bar. Okay. So now we could say something like this. We say the sample population squared is 1 over n, just like it was before. So squared. But now we're going to do it over here. 1 minus n quantity squared. that make sense? Oh, okay. I wasn't sure you were trying to keep yourself away. Okay, so what's the point of this? Why is this necessary? So when you're thinking about the standard deviation of the underlying population, right? You may be asking yourself questions like, okay, did I just get a flaky batch of data? Like, was this data just had a, much wider spread than all of the other stuff? Because sometimes random things happen. And as you go to look in the homework this week, you'll notice the first question I asked you is how do you, like, what type of things do you see about the data that might be suspect? So we want to remember that anytime that we're doing statistics in real life, right? We talked about this a little bit in computational. There's always other forms of error that can creep in. So we measure things with instruments. Human beings record numbers, right? So there's always potential for things to go wrong. So as we look at these populations, we can't simply say, okay, I measured the standard deviation once, and so therefore I understand the underlying uncertainty. Because if it's truly something that is generating this random distribution of numbers, especially if you don't know the mean, right, then it's going to be much more difficult to calculate the standard deviation first, at least have an estimator for the standard deviation, right, that's unbiased. Good.
That's what we said. That's what.
Yeah, this can be S squared, because this is the real thing,
Oh, so there's some.
but you're kind of stuck with this like hodgepodge, which is an approximation. So that's kind of similar to what we showed over here, right? But this would be like the sample mean attempting to describe the true population, right? And this would be great. This would be the sample variance. But instead we get this one, which is a version of that when the mean is. Okay. Lost anyone? Okay, probably just gonna write this up here. Just as a result, and you're welcome to go through it if you like. If you really want to, we can go through the idea of biased and unbiased estimators. So we can talk about the fact that, the things that we're creating here, some of them are really true, the underlying population, and some of them, they have issues. But generally speaking, the population standard deviation, as we said here, will just be defined like this. This is going to be very annoying to you, Matt, perhaps. So, here's your sigma quantity like that. It's going to be the square root. Estimator squared. Is that annoying or not?
No.
Okay, so this can be either one of these, right? So at the end of the day, this estimator for your population uncertainty is as large as the uncertainty of the data itself. Population standard deviation. Getting a lot of sleepers. I'm sure. No, it's fine. One of the problems with this section, and that I mentioned it at the very beginning, right? As we get into the math part of this, right? I was like, how do I keep folks engaged? Like, I was thinking, okay, do I bring the cards in and like have you bet on them? Okay, that's fine. So, let's see. We had this worked example. Should we try and do the sample standard deviation? Oh, I'm gonna erase it.
Wait, quick question. Now, sometimes in the parentheses of the form over there, where does that go to? Negative X
This, oh, sorry, this piece here.
Oh, that's one whole thing.
Yeah,
Okay.
you just run
I didn't write up a funky. But this is EXP, right? This is like E to the,
it. Yeah. No, you didn't write it, okay, it's just like it's,
Yeah, I just thought.
It's
like a thought bubble of the E.
Yeah.
Yeah. Okay, yeah, we probably have time to start this. So you still, do you have that data that was written down?
no.
Yeah.
The
Tell me no.
The height and weight, yes.
Okay, so what I'd like to know here is, we have means for X and Y.
You should.
I have for X, I wrote it down. What is it? 175, 170.
I can do one.
Good.
Divided into 66.8.
Say that again?
For the Y, it's 66.8.
Yeah.
For the B.
Yeah, good. Okay, so now what is the standard deviation for both of those populations? You have that? Cause I wanna think about them in terms of these estimated parameters, right? We have this, two thing data set. Right? So let me write this.
Do you want to send deviation? Yeah.
We got.
The sample variance for X, it should be 175.8.
Standard deviation.
So the
So
Y-
standard deviation for X, I got 11.
It should be, the variance would be S squared
That I got 11.56.
for X. And this one,
Wait, so,
I'm gonna ramp it if that's okay.
yeah, just making sure.
I did.
Really, my problem is really good.
Want to take the square root?
Yeah, I think it's recruited.
Just multiply it by 1. Okay.
Multiply by 176.58. Yeah, that's. Yeah, that's what I'm thinking.
Mine, they were like, -40,000.
Yeah, that's, okay.
I'm gonna put the answer up here, it's 10.6. Okay, so you might look at these numbers. And, you know, if you didn't take any data analysis classes, if you hadn't taken any statistics classes, how would you report the uncertainty on the mean that you calculated? So first you would write the mean, right? Okay, 175.5, 175.7, boom. And you just hand that to your boss, right? Okay, is there uncertainty in your answer?
There should be.
There should be, why?
You have that sample variance.
Yeah, not only that, did you sample the entire population?
No,
No, and you have no access to it, right? Okay, so what would your first instinct right here be?
it would be,
175, 7 plus or minus 11.6.
Good, so 175 plus 11 point like this, right? Right, that's a very good instinct, and that's probably maybe And yeah, it's definitely wrong, but it's a first good instinct, right? Because we said actually over here. Right, that S. Let me write this. Right? That the uncertainty associated with the mean should go like the standard deviation divided by the square root of n. And one little caveat, so let's put a little asterisk. Would be if sigma is known. Right? And if it's not known. You get sigma. And you can just believe me, okay? So what does that mean? That means you, yeah,
You don't know it.
sorry. Good eye, very good eye. Okay. So we're gonna not write it like this, we're gonna write it like that. Okay. And similarly, how would you write this one?
Same thing. Applies when it's-
Good. Okay, so let's pause there before we calculate the rest of these uncertainties on the standard deviations and whatnot. But you begin to see how we'll be using this for the populations themselves? Okay, so we're not just handing people means anymore, we're also trying to indicate how certain we are in those means. Okay. And as n gets really large, you can even see it here, standard deviation on the mean, right? Uncertainty on the mean. Question, comments, concerns?